Hello and welcome. Today we're going to be doing a simple example of a double integral using polar coordinates. Okay, so let's go through the example. We're going to say that f of x comma y is equal to x squared minus y squared. This is the familiar hyperbolic paraboloid. And it's also what they call the Pringle surface. The Pringle surface because it has the shape of that potato chip. Let's now go in and try to figure out what we're going to do here, and we're going to basically compute it on this domain, which is going to be a unit. It's going to be a 1/4 wedge of. I'll write that 1/4 better. A 1/4 wedge of the unit circle. A 1/4 wedge of the unit circle, from theta is equal to pi over 4 to theta is equal to 3 pi over 4. Okay, so let's get a picture of what this looks like. Okay, here's x, here's y, and there's z. And we know that the hyperbolic paraboloid on the y equals 0 line is an upward facing parabola like that. But we're looking at a specific point here. We're looking at that unit circle wedge that sweeps out like that. And that's going to be from theta is equal to pi over 4 all the way to theta is equal to 3 pi over 4. So there's that 1/4 wedge, okay? So this is my set D that I want to integrate over. And on that set, of course, we know that in the y direction, we have a downward facing parabola, a downward going parabola in the curve. We also know that at the 45-degree line, the function itself, when x is equal to y, we know that when x is equal to y, the function's 0. So we know that the curve kind of drops down like that, and it'll come back up like that, right? So the surface is always beneath the xy plane, like that. So the surface is beneath the xy plane. Okay, so we expect when we do this integral, so what is our goal? We want to compute the double integral over f dA on this 1/4 wedge of a circle. Okay, all right, so we expect this to be, the volume to be negative. And I picked this example because it was maybe a bit odd, and also because I just wanted to show how we could determine this thing, a negative volume. So, of course, we're talking about all this space underneath of the plane here, all that volume there. Okay, so to get started, we're going to use polar coordinates. Because of course D is a circular wedge, so it's natural to use r and theta to describe D. So our tasks for all of this are always going to be, so of course we want to take this integral. And what we want to do, of course, is fill in all these blanks here. And again, we need to construct, the biggest goal here is we need to construct the iterated integral. Okay, in order to do that, what we got to do is we're going to use polar coordinates The first thing, of course, is we have to define D, the set we're integrating over, and we have to define it in terms of r and theta. Okay, so we can do that pretty straightforwardly. R has to go from 0 to 1, and theta is going to go from pi over 4 to 3 pi over 4. And by clearly defining this, you've essentially set the limits of integration. Okay, all right, so the next task we have to do, of course, is to figure out dA. We know that's going to be in polar coordinates, so we're going to use the r, dr, d theta polar coordinates. This is an identity you certainly want to memorize. Okay, and finally we have to define rx in terms of polar coordinates, which is going to be r cosine theta, and y is going to be r sine theta. So our integral, when we write it as an iterated integral, is going to be as follows. We're going to do theta, that integral last, so it's going to be from pi over 4 up to 3 pi over 4, and the integral from 0 to 1. And then we know that f is equal to x squared minus y squared, so we have to put r cosine theta, quantity squared, minus r sine theta, quantity squared. So we have that as our integrand, and then our area differential is going to be r dr d theta. Okay, so now we've finally figured out what the iterated integral is. The next step then is going to be computing it. So we're going to do that on the next page. So there's our integral from the previous page. What we're going to need to do, though, we're going to do a little bit of simplification here. We have an r cubed times sine squared theta, or sorry, oops, my bad. Cosine squared theta minus sine squared theta, dr d theta. And that's just by factoring out all of the r variables into their component. All right, so from here I can actually compute the r integral. Of course, this is basically a fixed constant in the r integral. And we're going to get the following. So when we evaluate this expression, the r expression, we're going to get a 1/4. So I'll just put that right there. All right, so the next step is clearly we're going to have to simplify this term, these set of terms using trig identities. All right, so there is a difference of squared trig function identity, but I always forget it. But I do have to remember there are a few that are really important to know, and once you know these few, you can always find the other ones, which is when you have a squared sine or cosine. So we know that cosine, and I'll write these in blue, cosine squared theta is equal to 1/2 1 plus cosine 2 theta. We know that sine squared theta is equal to 1/2 1 minus cosine 2 theta. So these are the double angle formulas, or some of the double angle formulas. Of course, we're subtracting them here. So in this case, those are going to cancel, and you're going to be left with cosine 2 theta down here. Okay. All right, so that, of course, is much simpler. We like that a whole lot. So now we can put that in And don't forget the 1/4, which we can put out front. And now the antiderivative of sine 2 theta is going to be 1/2 times sine 2 theta. And we're going to evaluate at our pi over 4 and 3 pi over 4 like so. And that's going to give us a 1/8 due to that 1/2 there. And then we're going to have a sine 3 pi over 2 minus sine pi over 2. Okay. So the sine of 3 pi over 2, that's -1, minus a sine of pi over 2, which is going to be just 1. So what we have here is -2 over 8, otherwise known as -1/4. So recall that we expected a negative volume based on the graph. And of course we found that negative there. So this is consistent with what we predicted ahead of time. So with this problem, I think it was a fairly straightforward problem, but it did involve all the important steps, both some integration involving some trig functions, which are invariably going to show up when you're using polar coordinates, as well as making careful observations of the graph, as well as constructing the iterated integral and swapping out all the Cartesian coordinates for polar coordinates. All of those are important skills that you have to deploy in order to use polar coordinates. This problem would have been much harder to do in Cartesian coordinates. It was a much more straightforward problem using polar. So I hope you enjoyed this video. I'll see you in the next video, and I'll do more examples.